Okay. So then the second one is a case where you're given a difference equation and you want to find some information about it. And the difference equation that you're given happens to be a filter, okay? And it happens to be a filter, a pretty good filter, because it has a zero. It happens to have a zero residing on the unit circle, which if you travel around the unit circle, when you get to that point, the response will be zero because you have a zero there. So it'll remove the whatever frequency is that it's at. So it destroys that. So it'll just remove it. So it filters out that particular frequency. And that's the nature of the beast. So y.2 is you have a filter. Y of n is described by x of n minus x of n minus 1 minus 0.9 y to the n minus 1 minus plus 0.081, I'm guessing, y to the n minus 2. So that's a digital filter, and it has a pole at 0.9. You can see that that's going to factor into that.
Isn't it x n plus x n minus 1?
What's that? It says x of n plus x of n. Right. And you're also going to have a zero at minus 1, because when that thing gets transformed and you factor it out, it puts a zero at minus 1. So there's a zero at 180 degrees, and there's a zero at however that thing factors. I will find that out in a second. So it says, A, using freq z function. So you have the frequency z function, okay, requires b, a, and omega. So it needs the coefficients of the filter you're talking about up there. So it needs the denominator coefficients, and you need the numerator coefficient, and it needs to know where do you want this thing plotted. So it's going to plot basically the z transform evaluated on the unit circle, which is actually the DTFT. Okay? So you want to plot the magnitude and phase of the response and make use of this particular function that's available in MATLAB. All right? MATLAB. All right? So you need to get well, first off, you got to figure out what h of z is, right? So h of z, so you take the transforms and you get y of z is equal to x of z plus z to the minus 1 x of z minus 0.9 z to the minus 1 y of z plus 0.81 z to the minus 2 y of z. All right? So just taking the z transform of that stuff. And then you solve for y of z is equal to 1 plus 0.9 z to the minus 1 minus 0.81 z to the minus 2. That's right. Make sure that I got that right. Yeah. Plus 8 minus 0.9. Let's make sure we got this right. Plus minus. Plus minus. see what happens here. It seems to be backwards, but I guess it's not. And then I go minus 0.9y, that's what I got, and plus 0.81, that's what I got. That's what the thing is. So then you do that, and then you get you get b, and then you gotta get a. Well, this is 1 minus z to the minus 1 times x of z. All right. So then y of z over x of z is equal to the transfer function of z, which is the transform of the impulse response, is equal to 1 minus z to the minus 1 all over 1 plus 0.9 z to the minus 1 minus 0.81 z to the minus 2. Minus 2. So, I have to look this up, but anyhow. So once you have that, then what you want to do now is to identify the vectors v and a, so you can put them in this function here and have it zippity-doodle plot for you. So this is b is 1 and 1. Coefficient of this is 1, and the coefficient this is plus 1. The coefficient of that is 1, and then a is 1. Well, coefficients are 1, 0.9, and minus 0.81, which is at odds with what I've got there. Well, we'll just plow ahead here. All right. So you identified. You've identified the numerator coefficients and the denominator coefficients, and so now all you have to do is choose omega. And omega you want to take in small steps, so it generates 0 to 500. What do we have? Times pi, and divide that by 500. And so that just generates an omega vector for use here. And it goes from 0 over 500 times pi, which is 0, up to 500 over 500 times pi. So that goes 0 to pi. 0 to pi. And if you want to go from minus pi to pi, you could do that too if you want to see a whole period of what you got there. But it's symmetric, so you really don't have to, because you just get the mirror image. So that's sufficient. So then you can find out what h is, now that you know h using MATLAB. So in MATLAB you have to write the equation FREQZ BAW. Well, I guess that's what you use in MATLAB. So when you go back through here and write the MATLAB stuff, in order to get h, that's what you use, okay? And we'll do that at the end. Then, once you get that, what you actually want is the magnitude of h, is ABS of h. And you want the angle of h, which is angle of h. And then you want to make it into degrees. You want to change it from radians to degrees, so you got to multiply by that conversion factor. Okay? So those two MATLAB commands will generate the magnitude, and this will generate the angle. And now it wants you to plot. Plot. Then you want to do a subplot. Right, 2, 1, 1. And then you want to, you don't want to, do you want to plot? Yeah, you want to plot, because this is a continuous function of omega. So you want to plot omega divided by pi of h mag.
The word angle?
Mhm. And then you want to subplot plot 2, 1, 2, and you want to plot w divided by pi and h angle. All right. You want to do those two things. And in addition to doing those two things, you want to title the plots, and you want to put the axes on the plots, and you want to do a few more things than just what I did there, but I'm just covering what you get. And that will generate the two plots, subplot, and the two plots you get look like this. You have the magnitude plot up here, and you have the angle plot down here. Here's the magnitude, H mag, and H mag is positive, and it has it looks like this, some kind of crazy function like that. And this thing looks like, and this is the 0 line, and this is like 10 up here. This goes like this and goes down like that, and this ends up here. This is at 1, and this is 0, and this is omega over pi. So that's in pi units. That's the frequency in pi units. Right? And it looks like that and looks like that. And what it wants to know then, so you plot those, okay, so you see that. Then, that's that A, okay, for these, so you plot them, and you plot the magnitude, H magnitude, or sometimes it's written as that. And sometimes this one down here is written as the angle. The angle, and this is, what is this here? This is 0. That's 0, and this down here is minus 180. This is minus 180. That way down here is minus 180. I think there's a minus 90. No, minus 90, sorry. Minus 90. And it goes from about 0 to 10, the magnitude does, and that goes from 0 to minus 90. And a curve that looks like that. So those are sketches, and if you do it in MATLAB, you get nice plots. And then it says, annotate the plot to show the exact values of h omega and h angle at values of pi over 3 and pi. Well, it just so turns out that this maximum is this is pi over 3, which is on this plot is 1/3, and this is 1/3, okay? And that's omega over pi, so at 1/3 you have omega is equal to pi over 3, which is just what it's asking. And if you look on there, this value of the magnitude is something a little larger than 10. I don't know, it's 10.2 or something. So at this point it's 10.2, and the angle down here is supposedly, this isn't drawn right. This is drawn, it's supposed to be drawn like this, I guess. It goes like this. And the angle, from looking at the plot, if you do it very carefully, it turns out that the angle is minus, this is like minus 58 degrees, and this thing value is about 10.2. So that point is minus 58, and that point is 10.2, and that's at pi over 3. At pi over here, this thing is 0, no magnitude, and down here it's minus 90 degrees, okay? And that point there, So you have this point here, it's a value of 0, and this point there is minus 90. So at this point it's 10.2 and minus 58 at pi over 3, okay? So if you read it off a graph, getting these values of 1/3 and 1, well, 1 is easy because, but trying to find 1/3 on a graph and reading off what the values are is not, kind of tricky. So it's just as easy to do this. When you did this, you evaluated omega over this range, right? Well, in this case, you don't want to evaluate omega over that range. You just want to evaluate omega at two values, pi over 3 and pi, right? Pi over 3 and pi. So what you can do is, in order to get these values over here, you set omega equal to a vector that has pi over 3 is one of the values, and pi is the other, all right? So it's only two values. And then you type H is equal to FREQZ B, A, and omega, and just see what it prints out. And it'll print out, well, I mean, you could do that, and then you could print out the H magnitude, you know, absolute value of H. And you'll get two values for that. And H angle equals angle H times 180 divided by pi. And you'll get two values for that because your omega, this thing will produce only two values. It will only evaluate this function described by that difference, and note where omega is just those two values. So you can easily have MATLAB analytically figure out what those points are on that graph, and you don't have to rely on reading the graph necessarily. And when you do that, you know, these magnitudes, this comes out to be 10.2 and 0, and this thing comes out to be minus 58.2 degrees and minus 90. So that produces the magnitudes at the 2 points you want on the graph, and that produces the angle that you want on the graph, points on the graph, written as degrees. Why degrees? Because you put the conversion factor in there to change the radian measure to degrees. That's important, okay? So that's what you'll get. Okay, so that's great. And now it wants the, what does it want now? What does the problem statement say? Okay, generate 200 samples of the signal x of n and use as an input to the filter. Plot both the input and the output of the filter using subplot, label, and title plot appropriately. Okay, so now you have this filter that's described by this equation up here, and now you're going to have as an input to this filter x, which is going to be a combination of sinusoids, one of which is at an angle of pi over 3. And so it's going to have its magnitude multiplied by 10 and its phase shifted by minus 58. And the other is a sinusoid that's at minus pi. At minus pi, at a frequency of minus pi. So when that comes in there, it's going to be 0. It's going to be obliterated because its magnitude is going to be reduced to 0. And if its magnitude is 0, it doesn't make any difference what the phase is. You don't see any effect of that because there isn't any magnitude to plot. So, and what you want to plot then is the output of this filter when the input is the combination of sinusoids. So the first thing you have to do in part B then is you have to generate the signal, the input signal, right? So, you know, this is generate input signal, okay? So you have to generate an input signal, and how many points do you want? It says 200 or something. So n is equal to 0 to 200. X is equal to sine of pi star n divided by 3 plus 5 times